Hello, Math 119 students. Today we're going to talk about sampling distribution, section 7.1. So I'm using StatCrunch to demonstrate. First of all, you need to know what is a sampling distribution. Okay, so let's look at a distribution where we have a normal distribution. Let's say this is the height of adult men. So the mean for the height of adult men is 69 inches. So you can see we have a bell-shaped distribution centered at 69, and the standard deviation is 2.8, as it shows over here. So let's take a sample of size 5. Okay, we'll take one sample of size 5. So this is as if we were randomly selecting 5 men and asking each one of them what their height is. So you can see that here's our sample of 5 here in the second row. And the sample mean for the 5 men was 66.7 inches. So we have one sample mean of 66.7 inches. Well, we're gonna do this over and over again. We're gonna continuously take samples of size 5 from the population. Let's take one other sample. Here's our second sample of size 5. We got a mean of close to 70, 69.9 inches for our second one. Okay, we can do this 5 times. Basically, we're doing the same thing we just did, but 5 times. We're taking 5 samples of size 5, and each time we're computing the mean for each sample. So we're going to have 7 sample means when we get finished. And we are building up the sampling distribution. Okay, so now we can actually do this, the same thing 1,000 times. So what we're doing is we're going to take 1,000 samples of size 5, and for each sample we're going to compute the sample mean, and we're going to put all our sample means down here in the bottom row. Okay, so let's do that 1,000 times and see what it looks like. So what we're doing is we're building up what's called the sampling distribution of the sample means. Okay. Also, with the sampling distributions, you can take any statistic you like. We could have taken the standard deviation of each sample. We could have taken the median of each sample. But we're taking the sampling distributions of sample means. So we're taking the sample mean for each sample. So let's do it 1,000 times. And when we do it 1,000 times, you can see what it looks like. So the distribution, first of all, let's look at the mean. The mean of we have what, about 1,007 sample means. So we have 1,007 sample means. The mean is 68.9. So you can see that the mean is close to the population mean. The mean of the population is 69. So the mean of our 1,007 means is close to 69. And the standard deviation is 1.26. Let's do it 5,000 times. So we're at 4,000. Okay, now we have 5,007. So once again, now you can see that the mean of the sample means is even closer to the population mean, 68.99 inches. Well, that's basically 69 inches. And also, what do you notice about the shape of this sample? We call this distribution in green the sampling distribution. Well, the shape looks like also bell-shaped. Our population has a bell-shaped distribution, and the distribution of the 5,000 sample means has a bell-shaped distribution in which the mean of the 5,000 means is approximately the mean of the same as the mean of the population, and the standard deviation is smaller because 2.8 is the population standard deviation, and the mean of the 5,000 means, or the standard deviation of the 5,000 means is about 1.25 or 1.24. Okay, so now I want to do the same thing over again, but this time I'm going to take a larger sample size. I'll take a sample size of 30. And before I do it, what do you think will happen? What do you think it'll look like? Well, let's take one sample. Okay? So here we take a sample of 30 from the population, 30 men, and the mean was 69.27. Okay, now let's go ahead and take 5,000. See what it looks like. Okay, so here's 1,000, 2,000, 3,000, 4,000, 5,000. So what do you notice this time? First, we want to notice where the center is, what the mean of the 5,000 means is. And then we want to also notice what the shape of the green sampling distribution is. Well, the mean is, once again, very close to 69, 68.99. Very close to 69, which is the population mean. That's the mean of the 5,001 sample means. And notice the shape looks similar to the green one when our sample size was 5, but it's narrower. And that's because we have a smaller standard deviation. The standard deviation is 0.5. So it looks like when you increase the sample size, the you have less variation in your sampling distribution. Our standard deviation is 0.5, whereas when it was 1.5, I think it was 1.24 when we had a sample size of 5. Okay, so now I'm going to do it over again, but do it a little bit differently. So I'll do it over again. So now I'm going to change the distribution shape. So this time, the first time we looked at the heights of adult men, which have a bell-shaped distribution. Now I'm going to look at a uniform distribution. Okay. So a uniform distribution has a rectangular distribution like this one. Okay, so it goes from 0 to 50. So what this shows is that if you randomly select one individual from this distribution that has a uniform distribution, it has an equal probability of any number between 0 to 50. Okay, whereas a bell-shaped distribution, you have a higher probability that you select someone that's closer to the center, because the center is high. It's a bell shape, and the center is taller than the rest of the distribution. So if we take one sample, let's go with a sample of size 5 again. If we take one sample of size 5, so our observation had a mean. Our sample had a mean of about 20.2. Okay, so let's go for 1,000. Well, actually, we'll go for 5,000. Okay, so now let's look at the population mean for this one from 0 to 50 is 25. And notice that the mean of the 5,001 means is about 25.1. Okay, and the standard deviation, the population standard deviation, 14.4. The standard deviation of our 5,000 means is 6.4. So it's a smaller, less variation, smaller standard deviation. But what do you notice about the shape of the distribution? We want to notice what the center is, what the variability is, but what's the shape? Well, it doesn't quite look normal. It looks more sort of a triangular. Okay. Now we'll do the same thing over again, but we will increase the sample size to 30. Okay, so we'll take 5,000 with an increased sample size of 30. What do you think where do you think the center of our green distribution and the shape will be? Do you think it will be similar, like a more triangular shape? Will it be narrower? What do you think it will be? Well, let's see. 5,000. Okay, so now the shape tends to look, well, first of all, the mean of our 5,000 means is 25. It's about the same as the population mean. The standard deviation is smaller than when we had a sample size of 5. And the shape tends to look more normally distributed. It's not quite as triangular. It looks more normally distributed. In fact, it looks similar to the one when we had the normal distribution, a similar shape. Okay, I'll do it one more time for this video. But now I'm going to change the shape of the population distribution again. So now we're going to use a right-skewed population distribution. So we've looked at a normal population distribution. We looked at a uniform, which was the last one a rectangular distribution, which is uniform. Now this one's a right-skewed population distribution. The mean is 14.05. The standard deviation is 11.8. So now let's do the same thing over again. We took sample of size 5. Let's take 5,000 samples and look at the mean and shape of our 5,000 samples. So there's 1,000, 2,000, 3,000, 4,000, 5,000. And first of all, what do you notice about the mean? 14.0, the mean here is 14.1, very close. Okay. Standard deviation is smaller. But what do you know now? What do you notice about the shape? The mean is the same as the population mean. What about the shape? Well, it looks like it's a little bit skewed. Slightly skewed, like the parent population is skewed, highly skewed, and the sampling distribution is less skewed. It's more of a bell shape than the population, but it's still somewhat skewed to the right. Okay, so now we'll do one more last example. Increase the sample size to 30 and reset it. Okay, let's do 5,000 samples and see what it looks like. 4,000, 5,000. Okay, so now once again we'll look at the mean. Actually the mean is very close to the population mean. Right? 14.05 is the population mean. The mean of the 5,000 samples, 14.08. Standard deviation is smaller than when we had the sample size of 5. So we have less variability. But then what do you notice about the shape of the 5,000, the distribution of the 5,000 means? Well, to me, it looks narrow, but it looks somewhat bell-shaped. It looks like a narrow bell. Okay. Okay, so that's something worth noting. So when we had a sample size of 30 for a normal population or for a uniform population or from a highly skewed population, in all cases, the mean of the sampling distribution, the mean of the 5,000 samples is almost exactly the same as the population mean, and the standard deviation gets smaller as you increase the sample size, and then the shape of the sampling distribution becomes bell-shaped as you increase the sample size, and once you get to 30, it looks like it's pretty close to a bell-shaped distribution. Okay, so this is, we learned about sampling distributions. We're going to apply this to the central limit theorem, which will be in another video coming up. So we'll stop this video and then we will continue from here discussing the implications of what we just learned in the next video. So that's it for this video.